I'm going to start the recording and class has started. All right. Hello. Welcome to Thursday. Um, administrative administrative things are sort of the same as always. Um, PA2 was due a few days ago. The late due date is on Saturday. So if you haven't already completed that, or if you are unhappy with your score so far, please make sure to um, keep that in mind. Um, Problem set 5 has been released. That is due tomorrow. So I don't see very many submissions for problem 5 right now. Um, Make sure you take a look at that and get that sorted, get that taken care of. Um, Grades for problem set 2 have been released. So in particular, you can take a look at how you did, and you can take a look at if you want to file a regrade request or something like that. Same thing applies for problem set as same thing applies for regrade requests as did for problem set 1. Um, don't spam a bunch of regrade requests just in the hopes of getting some points back. Compare the rubric to the answer key to what you wrote, and if something doesn't match what you expect, then file a regrade. Um, yeah. Oh yeah, and then PA3 has been released. Hopefully the autograder for that should be up in the next day or so, but you have the PDF, so you can start taking a look at that. Um, and as always, ask on Piazza if there's questions or clarifications. Um, PA3 does use shortest path algorithms, which we will cover in class either today or tomorrow. So hopefully that should be helpful. Uh, that's all I got on the administrative side of things. Are there any questions? Are there any things that people want to talk about before we move on to content? All right. If there's nothing, let's get started. Reading whiteboard. Excellent. All right. So, past few lectures, we've been talking about graphs. In particular, we did definitions. We did a lot of definitions. We did representations. Um, and then yesterday we talked about DFS and BFS, right? So depth first search and breadth first search. Today, I want to sort of continue this discussion on depth first and breadth first search, and maybe use that in the context of other graph algorithms, other things you might want to do in a graph. So I want to start by motivating the following problem. I've been thinking about the right motivation to have here. Let's think about like um, let's think about a make file, right? In a make file, we have a bunch of targets. Uh, we have a bunch of rules that specify how to build each target. And um, these rules come with a bunch of like dependencies, right? Maybe I want to say like each target has a bunch of dependencies. Um, and so when we invoke make, right? When we try to build a particular target, um, we often end up having to build a bunch of other targets, right? So you might have like in your PA2 make file, um, you might have something like uh, PA2 is a target, and this relies on maybe PA2.0 and what was PA2? Oh yeah, like KD tree.o or something like that, right? Um, and then PA2, the object file might rely on the C, the source file, and um, maybe you have like a a utility header or something, right? And then maybe kdtree.o relies on the corresponding source file and also this utility header, right? So when we build PA2, the sort of the binary, the executable, we also have to build all of these targets, right? So when we build, we often have to build multiple targets, right? So the problem I want to look at today that we're gonna maybe use graphs to solve. What order do we build the targets in? Right. So um, some things to sort of note here are the order we build things in matters, right? I can't I can't try to build PA2 and then go on to build the corresponding object file, right? Because in order to build this, I have to have access to this object file to link it, right? So in particular, if I tried to do or if I tried to do something like if I picked a bad order, right? If I said, okay, I'll build the PA2 object file, then I'll build the PA2 executable, then I'll build the KD tree object file. This build step is going to use a stale version of this object file, right? So it's going to link against the wrong thing and you're going to get the wrong output, right? So in particular, the order in which you build things matters, right? So an example of a correct order is build the two object files and then build the binary. This is not unique, right? Because there's nothing that says I have to build this object file first. So I could also build kdtree.o and then pa2.o and then pa2, right? There's many possible orders, but there is this like notion of a correct order and an incorrect order. So in particular, um, for correctness, we require that, or the constraint that we can put on this, all of a let's say a target can only be built after all its dependencies, right? So here, um, the PA2 target can only be built after these two object files have been built. The PA2 object file can only be built after the source file and the utility header are both available, right? Um, so a target can only be built after all of its dependencies. Um, okay, so hopefully this sort of motivates a problem, which is we have a bunch of things, some of them depend on each other, and we need to find a good way to schedule them, right? Uh, the the name of this sort of problem, or I guess maybe I'll start by sort of describing how to model it, right? So we can model this as a graph. To define a graph, I need to tell you what the vertices are and what the edges are, right? So there's one vertex for each target. And let's say there is an edge from U to V if U, um, sorry, if V depends on U, right? So the graph that corresponds to our make file here is, I'll draw maybe the executable at the bottom. Um, there's an incoming edge for each of its dependencies. So there's an incoming edge that corresponds to pa2.o, an incoming edge that corresponds to kdtree.o. For pa2.o, there's an incoming edge that corresponds to uh, the source file. For kdtree.o, there's an incoming edge that corresponds to the source file. And for both of these, there's an incoming edge that corresponds to the utility header. Right? Does this make sense to everyone? Do you see how we get this graph from this make file? Or I guess, are there any questions so far? Right. One way we can think of this make file is this is sort of giving you a adjacency list for a graph, right? Right. You can think of the list of targets as like an array of vertices, and then for each target, the list of dependencies is like a linked list of vertices that are adjacent to it. Except for an adjacency list, normally you record the outgoing edges. Here we're recording incoming edges, right? So maybe I'll put this in quotes. Right. So based on this makefile, we build this graph. Now I can rephrase the problem as I want to order maybe I'll say I want to sort the vertices of a graph, in particular this graph, such that for every edge u to v, u comes before v, right? And then for a definition, such a sort is called a topological sort. Right. So in particular, we're going to be looking at the problem of topologically sorting a graph, right? Now, it turns out that not every graph can be topologically sorted. Well, okay, maybe I want to write down some important properties here, right? So first of all, a topological sort if it exists, is generally not unique. The other thing I want to say is a topological sort may not exist. Can anyone tell me, um, or can anyone describe a graph for which a topological sort doesn't exist? Or for like, describe a graph where it's not possible to order all of the vertices such that a predecessor always comes before its successor. Describe a graph or describe a property of a graph or sort of like um, relay to me the vibes in which the second one is not possible. Robert says cyclic. Exactly. That is exactly correct. If your graph is cyclic, then we get the following set of constraints, right? I've got something like this. A has to come before B, which has to come before C, which in particular implies that A has to come before C, but this edge says that C has to come before A. And so that's a violation. So yeah, maybe I'll say it exists if and only if the graph is acyclic. Oop. Right. So our example graph here for the make file, this is acyclic, so we're good to go. So we can topologically sort it. Um, we're going to look at two algorithms for topological sorts. Oh, sorry. I guess before I go into the algorithms, attendance poll question for today. What's your favorite application of a topological sort? Sort. Maybe we'll like whirlwind through a couple other things, right? So obviously we've got like I guess in general, anytime you've got a bunch of stuff and some things depend on other things and you want to schedule these things, the thing that you want is a topological sort. So for example, we've got a make file with targets, right? You could think about like scheduling classes with prerequisites, right? So you've got a bunch of classes that you want to take or that you need to take. Some classes are prerequisites for other classes. We hope that there's no cycles in the set of prerequisites, and you want a good order in which you can take classes. And then my favorite one is like instruction scheduling, right? So your compiler takes code or takes like high level code or whatever, turns it into a bunch of instructions, like assembly instructions. These instructions might depend on each other. So I might have like the I might use the output of one instruction as the input to another instruction. So there's a dependence there. Um, Now I can schedule these instructions. I can write them down in whatever order I want, as long as all of the outputs are computed before they're consumed as inputs, right? So one way of framing instruction scheduling is I can build a giant like dependence graph um, of all of my instructions and then topologically sort it. In the real world, in in insofar as the compiler world is real. But in the real world, you might care about more than just topological sorts because you might have like um, you might have an instruction that takes like a very long memory access, and so you want to schedule it early so that by the time its result is consumed, the memory access is available or whatever. So you might want to do like type-based scheduling or something like that, but we're not going to talk about that here. This is not a compiler's class. Um, so yeah, in general, any sort of thing where you want to like schedule a bunch of things that depend on each other and you want to make sure that the dependencies are satisfied. Um, I realize that's essentially an answer, but tell me about your favorite one. Okay, so let's talk about topological sort algorithms. Uh, there's two that we're going to talk about. One of these is based on depth first search. The other one is called Kahn's algorithm, which is based on essentially a breadth first search. Right. So this one has DFS vibes in particular because it's essentially doing a DFS. This one is Kahn's algorithm. It's not quite a BFS, but it has very BFS vibes. And hopefully that'll make more sense when we talk about it. Okay. So let's start by looking at the DFS based algorithm. Maybe the first thing is to recall the pseudocode for a depth first search. Does anyone in the chat want to, let's say, help me recall the pseudocode for a depth first search? Maybe I can get you started, right? We had DFS on a graph says for each vertex in the set of vertices, um, if V is unvisited, I'll visit, right? So the sort of interesting part happens here, right? What did we do to visit a vertex? I think we used the letter U for this. What's the first thing we do? Increment time and marked visit time. Yeah. So we can say um, the discovery time of U is, I'll just say plus plus t. Maybe we set t equals 0, right? So we mark the time that we first enter the vertex U, and then for each oop, for each edge from U to V, if V is unvisited, we recursively visit V. And then what do we do after this for loop? We record the time we were finished with U, right? So we increment the time and record the time that we were finished. Now, it turns out, um, the important part of oh, sorry, and we mark like mark the oop, mark V as visited. Right. So the important part of DFS is this sort of recursive procedure here, because the only thing that our like top level function is doing is making sure that if we have multiple possible routes, we hit every possible route. Okay, so the idea of using DFS to do a topological sort is we can sort of hijack this function, right? I'll say like push vertices onto a stack, right? So in particular, we want to make sure that uh, all of the dependencies have been scheduled before we schedule um, a vertex, right? That before before V gets scheduled, all of its dependencies have already been scheduled, right? So in particular, we want to make sure that a dependence is scheduled before all of the things that it depends on, right? That's sort of another way of saying this is like if I have a graph where A is a dependence for B, C, and D, I have to make sure that A gets scheduled before any of B, C, or D, right? Because if that weren't the case, then we would have this inverted condition where, like, let's say C gets scheduled before A, and that's bad because A is not available at the time that C is computed. Or the like you don't satisfy a prerequisite for C, right? Or something like that. So maybe I'll continue and I'll say a vertex must be scheduled before everything that depends on it, right? Maybe we say it must be scheduled before all of its consumers, right? We can think of this as like producers and consumers. So like B consumes the result of A, C consumes the result of A, or something like that. Okay. So given that we want to sort of schedule things, push things onto a stack while maintaining this property, we notice that U as a vertex has, potentially a bunch of consumers. Um, Here in this inner for loop, we loop over every consumer of U, right? Like every iteration of this for loop, every V is a consumer of U, or is like something that depends on U. right? So if we sort of um, if we think of like the secret purpose of visit is to put you in the right place, then after all of these recursive calls to V, we know that all of the V's have been scheduled, right? And so once all the V's have been scheduled, we are free to sort of schedule U before all of them, right? So the way we're going to do this is we're going to augment our visit function to take an extra stack as a parameter, right? And we're going to sort of thread that stack through all of the recursive calls. And then once we're done with all of the recursive calls, once we look at the time that U was finished, we're going to go ahead and say stack, or we're going to say push stack comma U, right? Does this make sense? So pushing it means we put it at the top of the stack, which means that it comes sort of before everything else that was already in the stack. In particular, everything that was in the stack includes all of the vertices V that had an incoming edge from U, right? So um, by the time, so in this example graph, right, by the time we get to this line of pushing A to the stack, we know that we've already visited B, C, and D and returned from those calls to visit. So in particular, we know that B, C, and D are already in the stack, right? So these might be here in any order, but we know that if we push A to the top of the stack, it's necessarily going to be above all of them, right? So we know that this sort of maintains the topological sortedness. Do people think it's valuable to work through an example of this? Or I guess a better question is, does the algorithm sort of make sense? Like, do the vibes here make sense? Does the idea kind of track, or are there questions? All right. If there's no questions, maybe we can do an example. Okay, so I'm gonna redraw the sort of makefile graph that we had from before. And we can try topologically sorting it with a depth first search, right? So makefile graph, I'm not going to write out the names of the targets, but we had A, B, and C, D, and E, and then F. Right? And it was something like this, right? This is a perfectly fine directed acyclic graph, or a DAG, right? If you remember from the definitions from Tuesday. Um, but yeah, okay, so we can think about topologically sorting this, right? Maybe I'll ask people to help me out here, um, and kind of tell me the next step that the DFS algorithm takes, right? So obviously we start by I'll keep track of the call stack here. And then I'll keep track of the sort here. Okay. And the top of the stack is down at the bottom. Just because it is. So that I don't have to. Actually, that's dumb. We can make the top of the stack at the top, right here. Okay. So we start by visiting A. Right. What happens next? We mark A as, or we sort of mark the discovery time of A. Maybe I'll scroll back up to the pseudocode if it's helpful to look at. You can shout it out or put it in the chat. So we're calling visit here, right? Where this is A. So we've obviously set the discovery time for A. Where do we go in the pseudocode? Any thoughts? We go to all the dependencies. Yep. So in particular, on this graph, what's the next node that we visit? Or what's the next like call that we push onto the call stack? Does anyone besides Robert have an answer? Maybe I should ask, is the lack of an answer a function of not understanding depth first search, or is it a function of the fact that it's 9:30 in the morning? Because if it's the former, then I would like to go over DFS again. If it's the latter, I'm not going to pretend I don't get it. It's too early, zero thoughts. Okay, I respect that. I wasn't paying attention very well. The boys season finale dropped this morning. Okay, I respect that maybe slightly less, but thank you for your honesty. Um, 3 a.m. here, no thoughts. Okay, that I very much respect. Okay, that's fine. So yeah, we visit the things that that depend on A, right? So in particular, we notice that there's an outgoing edge from A to D. So we're going to visit D, right? We've marked the entry time for D. So now we look at all of the outgoing edges for D. In particular, we see F. So we visit F, right? We mark the visit time for F, or we mark the discovery time for F. We look at all of its outgoing edges. It turns out there are none, so that for loop finishes, and then we move on. We look at the return time, or the time that it's finished. We mark that down. Not going to care about that here. And then just before we return, we push F onto the stack. Right. And then we return. So now we're back to D. we look at any other outgoing edges. Oh, I guess we should mark F as being visited, right? So we mark F as visited, and then we pop up the stack back to D, right? Are there any other outgoing edges from D? There are not, so we're done with D. So we push D onto our sorted stack and return back up to A. Any other outgoing edges from A? There are not, so we push A onto the stack and return back, right? Now we continue on to B. I guess we'll mark D and A as visited. We continue on to B. We visit B. Similarly, we look at all of the outgoing edges. We see one to D, but D's already been visited, so we don't recursively call it. We see one that goes to E. That one's fine. Let's visit E. Now we look at all of the outgoing edges from E. There's one to F, but F's already been visited, so we don't do anything there. Now we're done with E. So we're going to push E onto our sorted stack and then return the call back up to B. Mark it as visited. B has no more outgoing edges. We've looked at all of them. We mark B as visited and push it onto the stack. And then finally, we continue our top level for loop. We visit C. It's got one outgoing edge to E, but E's already been visited, so there's nothing to do. So we terminate that for loop. We mark C as visited, and we push C onto the stack and return from this call to visit, right? And so the final topological sort is C, B, E, A, D, F. And you can sort of see, you can sort of notice that the arrow from A to D, the arrow from B to D, the arrow from B to E, the arrow from D to F, the arrow from E to F, the arrow from C to E. All of these arrows sort of go forwards, right? So this particular ordering of vertices is a valid order in which to compute things. Yes? Does this make sense? Cool. All right. So DFS is good, right? Or DFS for topological sort is good, because we sort of get to use DFS, which we already have. This also, like DFS gives you finish times, right? Start and finish times, or discovery and finish times. And something to notice is like the uh, the vertices here are sorted in reverse order of finish time, right? Necessarily, because when something finishes, we push it onto the stack. When something else finishes, we push it to the front of the stack or the top of the stack or whatever. And so the thing that finished most recently is going to be at the top of the stack. So this is going to have a highest finish time. This is going to have the lowest finish time, right? So like something that you could consider doing is running a DFS, getting all of the finish times, and then just sorting by finish time. Although, of course, that would be bad because the DFS itself is B plus E, and then you want to resort things. So that's V log B, right? So from a complexity perspective, that's bad. But the fact of the matter is, DFS does give us this notion of finish time, right? And so if we want to use that in our schedule somehow, or if all we really care about is like, did two things um, finish at the same time, or did like what has to come first, or something like that? Um, you sort of get this extra this nice metadata, right? The one thing that DFS doesn't let us account for is the fact that in the real world, right? Um, if we're scheduling a bunch of things that look like this, if we're scheduling a bunch of things based on like this graph, right? We maybe care about putting A, B, and C first, right? Not for any like good, um, not for any good reason, right? It's a perfectly valid topological sort what we did here, where we sort of do F, then D, then A, then E, then B, then C, right? Like kind of going up the lines like this, right? That's perfectly fine. But if you think about like taking classes, right? You um you sort of might care about the fact that you can take these three classes at the same time, right? Rather than taking this and then taking this and waiting before you take this, right? This particular topological sort uh, kind of says, okay, you could take C and B at the same time, and then you have to take E, and then you can take A, right? So we kind of give up we give up the fact that if we could take three classes at a time, we could complete this entire schedule in three steps, right? Or if our make file has access to a bunch of threads, we could we could sort of build A, B, and C simultaneously. And then once they're done, build D and E. And once they're done, build F, right? So we could build this faster, right? This is sort of what if you've seen this like J flag, you say like make dash J 8 or something like that. It's going to use like 8 separate cores. It's going to compile 8 things at once. So we're not taking advantage of that. Or in the compiler world, right? Maybe you have a like a superscalar processor, right? And so we can sort of have this instruction in flight and still schedule this one and still schedule this one. But if our sequence of instructions looks like this, then we can schedule C and B at the same time. But now E has to wait for both of these to be done before we can schedule A, which means that the entire thing might take longer. Right. So DFS is nice because it gives you this, I mean, it works, right? It gives you the correct answer. It's also a great way of detecting cycles because if we ever find a back edge, right? If we ever find a back edge while we're doing DFS, we know that there's a problem, right? If you remember, a back edge is we're looking at a particular vertex. We're looking at some U. We look at one of its dependencies V, and we notice that V is marked as currently being processed instead of done being processed, right? So it's sort of going up the chain. Um, and so we know for a fact that that means that there's a cycle, and so we know that this thing can't be topologically sorted, and so we can sort of error out early. Uh, Han's algorithm is the breadth first search based version of topological sorting. So the idea for Kahn's algorithm is, first of all, we notice, like, as I've sort of said already, right? A, B, and C are vertices that can immediately be scheduled in any order that we care about. It doesn't really matter what order we put these in, but we can immediately schedule A, B, and C, right? Um, what is it about A, B, and C that makes them schedulable in this graph? What property? Any thoughts? Right, so we notice that the number of incoming edges for A is 0, right? The number of incoming edges for B is 0. The number of incoming edges for C is 0. In particular, this means that they don't depend on anything, right? So they can be scheduled right away. So the idea of Kahn's algorithm, schedule based on the in degree. Now, I actually can't remember. Did I define the degree of a vertex or the in or out degree of a vertex? Do people know what this means, or should I define it? I mean, very simply, for an undirected graph, the degree of a vertex is the number of edges incident to it. Right? For a directed graph, the in degree is number of incoming edges. The out degree is the number of outgoing edges. Right? Just definitions. So when I say schedule based on in degree, I mean schedule based on the number of incoming edges we have. Right? So we can start, and I'm going to redraw this graph for the third and hopefully final time. Okay. We can start by sort of annotating every vertex with its in in degree, right? Um, so that looks like a little 0, 0, 0, 2, 2, 2. Right. Now we um, and we care about vertices with an in degree of 0, right? We should always have a vertex with an in degree of 0, unless the graph is cyclic, right? So we sort of care about removing vertices in the order that they're in order of like lowest in degree, right? So we can start by insert all vertices into a priority queue based on the in degree, right? And then we can say while the queue is not empty, we dequeue something from our priority queue, right? We check that the degree, maybe I'll just say check, the degree of v equals 0. And then we'll say schedule v and remove v from the graph, right? The idea here is the graph, instead of tracking all of the targets, it tracks the targets that we have yet to build, right? So if we start by scheduling A, we remove A from the graph. In particular, this means that the in degree of D goes down to 1, right? So removing V from the graph entails each edge V to W, decrement the degree of W and reinsert into the priority queue. Right? Or more generally, we sort of know that right, remove V from the graph and just keep doing this until the queue is not empty, right? So what's going to happen here is we dequeue the A, we dequeue a B, or we dequeue the A, which sets maybe I'll keep track of this and I'll just say the degree of D is now 1. We dequeue a B, which sets the degree of D to 0 and the degree of E to 1, right? We can dequeue the C, which sets the degree of E to 0. Now we've got D and E available. So we dequeue the D, which sets the degree of F to 1. We dequeue the E, which sets the degree of F to 0. And then we dequeue F. Here's our sort. Of course, we could have swapped these two around, right? Because once we'd finished with A and B, both C and D had a degree of 0. So it was sort of a choice of which one we choose to dequeue. But the idea is we could also, instead of what's the word? Instead of dequeuing these one at a time, right? We could scan over everything, and if we've got access to like scheduling things in parallel, schedule everything with a degree of 0, and then remove all of those vertices at once in one step, and then schedule everything with a degree of 0, remove all of those vertices, and then schedule everything with a degree of 0, right? We could do something like that. You might notice, strictly speaking, you don't really need a priority queue here, right? Because the only time, like, you can do something like keep a work list of, or maybe just keep a queue of things with a degree of 0. And every time you decrement the degree of a vertex, you check to see if its degree becomes 0. If it does, you insert it into the queue, and then you sort of just keep processing things in the queue, right? So instead of this, we could say, maybe I'll say like work list, right? And here, maybe instead of this, I'll say insert V such that the degree of V is 0 into a work list. And then here, grab a vertex from the work list, right? So now we don't have to deal with this like heapifying and this log n thing or whatever. And this works perfectly fine. This Kahn's algorithm kind of, or phrasing it as a work list kind of mimics what you might do in like a distributed system or in a system where you've got access to a bunch of threads, is you literally put these into a work list. You've got a bunch of threads that like pull this work list, and every time you see something with a degree of 0, you say, okay, great, I can start working on this, and the thread just grabs it and starts working on it, and then decrements the degree of everything that that depends on it, right? And so the next time another thread is finished with whatever it's doing, it comes back to the work list and looks to see if there's anything with a degree of 0, and then grabs it and then keeps going, right? And so this way we sort of like, we get to schedule things in parallel almost for free, just because if there's enough available threads, they'll kind of grab all the right stuff and they'll kind of go off and do their thing. All right, it's 9:42. I am going to call it here. If there's questions, I'm happy to stick around and answer them. But otherwise, you are free to go. Don't forget the attendance poll. Tomorrow, we're going to talk about shortest path algorithms. I will stop the recording and